Hello everyone. In this class, I will talk about the experiment of measuring Lamor frequency with a hard-pulsed FID sequence. First, let me introduce you to the pulse sequence. Pulse sequence can be divided into two classes according to the type of excitation. The first type is selectively excitation IF pulse, and the second type is non-selective excitation IF pulse. The selectively excitation IF pulses are also known as soft pulses. The characteristic of the soft pulses are first, in the time domain, the duration of soft pulse is relatively long, generally in the order of 1 to 10 milliseconds. When we talk about MRI later, we are going to use soft pulses. In MRI, the soft pulse we set is about 1200 to 3200 microseconds. That is between 1.2 millisecond and 3.2 milliseconds. Due to the long duration of the soft pulse, the intensity is relatively low. Second, in the frequency domain, the frequency band of soft pulse is narrow, roughly in the range of kilohertz. So the soft pulse can selectively excite the signal in the frequency band. The spectral positioning of MRI is accomplished by using gradient magnetic field and soft pulse selectively. For example, we apply a soft pulse here. It doesn't excite the whole sample. Combined with gradient magnetic field, we can select layers like this. Select a layer to activate the signal in the layer. The signal is extracted and spatially coded to produce a two-dimensional MRI. We won't talk about it today, but we will talk it later when we mention the other experiments. The second part is the non-selective excitation of IF pulses, also known as hard pulses. The main characteristics of the hard pulses are first, in the time domain, the duration of hard pulse is short, generally less than 30 microseconds, and the intensity is relatively high. And second, in the frequency domain, the bandwidth is so large that can excite a wide range, so it is non-selective. That is, after the sample is placed in the probe. In the probe, we use a hard pulse to excite it. It excites all the spin nuclei in the sample within the probe. It excites the whole sample, and we get the signal from the whole sample. Such non-selective excitation pulses are commonly used in relaxation analysis and three-dimensional magnetic resonance imaging. Earlier, we introduced the type of pulse frequencies. I now introduce the hard pulse FID sequence. I followed this sequence diagram. There are several aspects to this sequence diagram. This line up here is the time axis, corresponds to the pulse frequency. This line down here is also a timeline, which corresponds to the signal that we picked up. This corresponds to the time applied by the pulse, the time collected by the signal, and the waiting time. This waiting time is the interval between the application of the first 90-degree pulse and that of the next 90-degree pulse. So let's look at the diagram. First, we apply an RF pulse with a certain frequency, a certain amplitude, and a certain time p1. When we set these parameters, the pulse deflects the longitudinal magnetization vector by 90 degrees, which we call a 90-degree pulse. That's 90 degrees right here. The applied pulse deflects the longitudinal magnetization vector by 90 degrees. Deflection into the XOY plane. This is called the transverse magnetization vector. In the later experiments, I will also show how to adjust the pulse to 90 degrees. And after P1, at this position, we turn off the RF pulse. At this point, the RF pulse ends. As we explained before, the magnetization vector after the deflection returns to its previous state. During the recovery, the magnetization vector causes a change in the magnetic flux in the probe, resulting in an induced current or induced electromotive force. The probe can receive an MRI signal. This signal, if you don't do anything with it, this is an oscillating signal and a decaying signal. The frequency of the oscillation is equal to the Lamor frequency. The decay is exponential. We call it FID signal, the free induction decay. If the MRI instrument receives this part of the signal and does not process it, then the oscillation frequency of this signal is equal to the Lamor frequency. The signal decays exponentially. If the FID signal is Fourier transformed, its central frequency should be the Lamor frequency. This is the hard pulse FID sequence. As we said earlier, the oscillation frequency of the NMR signal is the Lamor frequency, and it decays exponentially. But in reality, the oscillation of the signal measured by an NMR device is very low. It's nowhere near the Lamor frequency, and it doesn't even have an oscillating signal. Why is that? First of all, we need to know about the laboratory and the routing coordinates. The longitudinal magnetization vector is deflected by 90 degrees when we apply a 90-degree pulse to it. Turn off the 90-degree pulse and the longitudinal magnetization vector will return to its original state. The recovery process has two parts. One is the longitudinal recovery, one is the lateral attenuation. Our probe can only detect changes in the magnetization vector in the transfer direction. We analyze it at a transverse magnetization vector. Attenuation of the transverse magnetization vector decomposes in the two parts. The first is that the transverse magnetization vector is moving in the circle around B0 at the Lamor frequency. The second is that the transverse magnetization vector will decay from the maximum value to zero, and the decay process is exponential. The whole process is like this, spiral process. If we look down from the above to the direction of the main magnetic field, we will see something very similar to this mosquito coil. Let's go, it goes from the maximum and then it decays in a spiral to zero. It's very similar to this mosquito coil. This is the oscillatory decay signal that we can see from the laboratory coordinates. The frequency measured in the laboratory coordinates should actually be the Lamor frequency. Suppose you have an observer sitting on an axis precession at the Lamor frequency. So this is the MRI signal in a rotating frame, and he just sees the signal going from the big to small, from big to small. The signal that we see in the MRI device is also such signals. It decays in accordance with tissue relaxation. Here, let me introduce you to the implementation of the rotating coordinates system. The rotating coordinate system is generally realized by the mixing circuit in the spectrometer system. Look at this graph. This is the NMR signal. This is the NMR signal, and its frequency omega 0 equals lambda multiplied by gamma multiplied by B0. We artificially set the center frequency of the IF pulse SF1 plus O1. After mixing, the frequency displayed on the MRI device is the difference between the two frequencies. This is the oscillation frequency of the signal that we measure. In this picture, for example, the signals detected have oscillate frequencies. This frequency is going to be equal to the difference between these two. In this way, we can observe the state of the oscillation by adjusting the center frequency so as to achieve the measurement of the Lamor frequency. Now let's look at the state of the MRI signal at different central frequencies. First of all, the current main frequency of this device is about 19. Is this one. Look at this one first. The current main frequency of this device is about 19.609 MHz, assuming that SF1 plus O1 is set at 19 MHz. No NMR phenomenon occurs in the sample at this time. Only noise is detected, and no signal is detected. There is only noise after the Fourier transform. Yeah, only noise. By adjusting the central frequency, such as we change it to 19.58 megahertz, it is closer to the resonant frequency, but this is the state of paranoid resonance. In this case, we can pick up the signal, but it oscillates at the higher frequency. And by Fourier transform, it deviates from the positive center frequency. When we modify it again, make it closer to the resonance until you end up with the Lamor frequency. There is no resonance, and then we will see how that works when we do the experiment. Okay, this is all about this course. We will share the experiment later. Thank you.